In this demonstration, we illustrate the main activities of the CHOReOS development process that go from requirement specification to choreography enactment. Considering the overall CHOReOS development process, as informally modeled in this picture, we will focus on the part of the process that goes from requirement specification to choreography specification, and from choreography synthesis and discovery to deployment and enactment. In particular, leveraging results achieved since the last demonstration at month 18, in this demonstration we describe how the highlighted development activities have been integrated, and for each activity, at the end of the video, we will point out the progress with respect to the previous demonstration. First, we look at the process of going from a requirement specification to a BPMN2 choreography model. For this month 24 presentation, we will focus on the latest work on using the requirement specification to retrieve relevant user task models, and then using these models to create an initial but partial choreography specification in BPMN2. Starting with the requirement specification, as covered in the month 18 demo, the requirements are used to retrieve relevant user task models to help inform choreography design. This example, which will run throughout the demonstration, features arrival handling at an airport. In simple terms, the cluster of requirements specified by the domain expert is matched to a catalogue of user task models called CTT models using a service called TEDDIE. The retrieved CTT models are then returned with the matched requirements. First, we will look at the XML request. The XML file includes the choreography name provided by the domain expert, in this case arrival handling, and the individual requirements with automatically allocated IDs. For example, functional requirement 6, the baggage handlers shall receive the updated estimated aircraft arrival time. Next, this cluster of requirements is imported into the TEDDIE service, which applies sophisticated information retrieval techniques to identify relevant CTT models. Each requirement statement is tokenized and pre-processed to disambiguate and expand its terms, for example, by applying hypernyms and synonyms. The natural language processing techniques seek to reduce ambiguity and improve completeness for the retrieval process. The expanded set of requirements is then matched to a searchable catalogue of generic user task models represented in XML. To do this, we build on a library of domain-independent models developed in S-Cube, the EU-funded network of excellence for software services. Within this catalogue, we have taken the commonly occurring class-level tasks, such as requesting and booking, and extended them with knowledge from the airport domain. Within the CTT models, each user task is specified with natural language descriptions of the task in context and the user goal achieved by completing the task. These descriptions facilitate the matching between the CTT models and the requirements. Finally, TEDDIE produces an XML results file containing the retrieved CTT models and the requirements that made the successful matches to each specific model. Before we move on to the results file, we'll take a quick look at one of the CTT models. This is the book stand CTT model. It follows a common three-tier structure we have specified. The top-level user goal book stand is decomposed into the interaction-level tasks such as input stand request. In turn, this task is decomposed into the application task level. Application tasks include retrieve flight data, retrieve the estimated time of arrival, and retrieve other data, which is optional. A set of rules to map between CTT and BPMN2 models has been developed for CHOReOS. For example, the enabling with data exchange operator denotes the boundary between tasks relating to one message exchange and tasks relating to another, i.e., it shows where one choreography task ends and another begins. Also, the choice operator and the request data re-input application task denotes the process flow back to the original choreography task. So, now let's look at the results from the TEDDIE service. The XML results file includes the choreography name and also the set of retrieved CTT models. Expanding the book stand CTT model, we have a description of the main user goal, the underlying subtasks, and the operators linking these tasks. In addition to this, we have a dedicated section for choreography. The choreography segment lists the choreography tasks and relationships derived from the CTT model using the translation rules. This information will be used to generate elements in the Magic Draw choreography model. Finally, we have the matched requirements. These are the requirements that identified the CTT model and are to be carried forward into Magic Draw. So, there we have the 5 CTT models retrieved from the requirements that were fired at the registry. Next, we look at importing the results into Magic Draw. First, we use the Cameo Interop tool to transform the XML file into a Magic Draw model. We set the configuration used for our transformation and select our file as the XML parameter. For the UML output, we select the same arrival handling name for setting up the Magic Draw project. When the configuration is finished, we can start the transformation. Once completed, we can now see the results in Magic Draw. We select the generated project and open it. The containment tree shows the matched requirements brought in from the CTT models and also the generated choreography tasks. We then create a blank diagram to populate with the choreography tasks. We can then drag and drop the choreography tasks to create the model. A degree of work is needed to arrange the elements, and the layout tool can help with this. Next, we need to add the relationships we imported. These include the sequence links between the choreography tasks and the return loops as specified in the translated CTT models. Again, the layout tool can help here. At this point, the choreography designer needs to review and enrich the diagram. Information from the CTT models is also brought over into the specific choreography tasks. For example, the Manage Landing CTT model is a broad air traffic control task which features 5 subtasks: Receive landing request, Confirm approach, Handle arrival strip, Calculate separation, and Handle arrival. For our choreography, we are only concerned with confirming the approach before booking amenities, so the choreography designer will need to amend this. We have also imported requirements related to the choreography tasks, which we can display in a dependency matrix. First of all, we need to fill in the information for the row. For this, we have the choreography tasks from the package called Demo. And next, we need to provide the details for the columns. For this, we define requirements as a type in the package called Requirements. Dependency criteria defines what relations to display in the matrix cells. We need to choose the trace relationship which was created between the requirements and the choreography tasks during the import from the XML file. The arrows show that requirements are tracing specific choreography tasks which can be checked by the choreography designer. So, we have now completed the first part of our demonstration. The completed model reflects the segments of the choreography we brought in from the CTT models as identified by the requirements. As you can see, the task names were used to help define the participants, and the tasks themselves were consolidated as Request, Book, and Confirm Amenities tasks. We now move on to the choreography synthesis process.
Now, let us focus on the part of the process that, through model-to-model transformations, goes from the BPMN specification of the choreography down to the synthesis of the coordination delegate artifacts. The coordination delegates, when deployed on the CHOReOS bus, allow for enacting the choreography by realizing the distributed coordination logic between the services discovered by the discovery activity. Since the synthesis process is central to the flow of the development process activities considered in this demonstration, In the following, this picture will be used to show step by step the interaction flow of the involved components and how this flow has been implemented. As a first step, the method startSynthesis takes as input the BPMN specification of the choreography and performs the model-to-model transformation that we have defined to derive the LTS-based specification of the choreography. We recall that this specification is called CLTS and this one is the derived CLTS as graphically represented by the GMF-based graphical editor we have implemented. We also recall that a CLTS is an LTS that, for coordination purposes, is suitably extended with fork and join constructs, conditional branching and loops. Currently, the transformation is partially implemented by means of ATL, which is a domain-specific language for realizing model-to-model transformations. Now, let us see how the automated synthesis process distributes the coordination logic specified by the obtained CLTS into the coordination delegate models. Starting from the CLTS specification of the choreography, the synthesis process extracts the list of the participants and, applying a further model-to-model transformation, automatically derives, for each participant, the CLTS model of the expected behavior with respect to the specified choreography. The CLTS model of the expected behavior is achieved by projecting the choreography onto the participant, hence filtering out those transitions and related states that do not belong to the participant. For each participant, this CLTS model specifies the interaction behavior that a candidate service has to support in order to be able to play the role of the participant in the choreography. Although the synthesis process is a batch process, we have also implemented an Eclipse plugin to allow developers to edit, visualize, save, project and simulate the extended level transition systems we have defined for CHOReOS. For instance, by using the feature for projecting CLTS offered by the plugin, the developer can easily project a CLTS with a right click on the file name. For the purposes of this demonstration, we will show only the CLTS projections for two participants, namely the airport and the airport speaker actuator aggregator. This one is the projected CLTS of the participant airport speaker actuator aggregator as graphically represented by the GMF-based graphical editor. In the same way, this one is the projected CLTS achieved for the airport participant. Note that this is a quite big model since the airport participant is involved in many tasks of the choreography and this implies to have a considerable number of states and transitions. Moreover, it contains many forking states, also nested, that make its treatment difficult, if not impossible, without being supported by a synthesis approach that is able to automatically calculate all the possible operation interleavings when interacting with other participants. Now, after a brief introduction of the discovery activity, we will see how the synthesis process and the discovery process interact with each other to retrieve from the service base those candidate services that are suitable for playing the participant roles required by the choreography specification, and hence those services whose behaviors is compatible with the expected behaviors as extracted from the choreography through projection. In particular, for each participant, the synthesis process interacts with the discovery service by performing the REST call to the discover services operation that takes the participant CLTS as input.
During the choreography synthesis process, the services that can play the different roles of the choreography must be discovered. This is the main goal of the service discovery activity that is realized by the abstraction-oriented service-based management. Today, and in the anticipated future Internet, we have a growing amount of services that may provide similar functional and non-functional properties. In this situation, the good news is that choreography developers may exploit these alternative options to develop their choreographies. On the other hand, the bad news is that the increasing amount of alternative options make their exploitation more complex. This is where service abstractions come into play. We employ service abstractions to facilitate the organization of the services that become available over time in groups, which consist of services that offer similar properties. We enable service discovery by issuing queries for service abstractions instead of issuing queries for concrete services. We distinguish between functional abstractions that group services with similar functional properties and non-functional abstractions that group services with similar non-functional properties. In the Math 12 demo, we showed the construction of service abstractions which takes place during the service registration phase. The construction of functional abstractions is based on a novel hierarchical clustering algorithm that we proposed in the context of CHOReOS, while the construction of non-functional abstractions is based on a novel partitional clustering algorithm that we also proposed in the context of CHOReOS. So, our starting point for discovering services for the managed unexpected arrival choreography is a set of abstractions that represent services that have been registered to the abstractions-oriented service-based management. These abstractions have been stored in persistent storage according to a relational schema that reflects the main concepts of the CHOReOS architectural style. Here, for instance, we have a functional abstraction that represents airport-related services. On the other hand, here, we have an abstraction that represents services that have to do with airport speakers actuators. Finally, these are the functional abstractions that group services with similar availability and response time. Service discovery is performed based on SBQL queries. SBQL is a language that we proposed specifically for CHOReOS. It allows to specify constraints on the properties of the services that we are looking for. The specified constraints are matched against service abstractions that represent available services. The result of an SBQL query is a set of abstractions that represent concrete services that can be used for the choreography. To discover services for the managed unexpected arrival choreography, a query is produced for each role. The query is based on the behavioral model of the role and specifically the operations that concern this role. Then the query is executed by the query engine that we developed in the context of CHOReOS, and the results are returned to the query author. The SBQL language is quite flexible as it allows to specify constraints only on the service concepts that we are interested in. So we may have a query that focuses only on interface level properties, or a query that focuses only on operation level properties, or even a query that focuses only on parameter level properties. In more detail, an SBQL query consists of variable definitions. Each variable stands for a service concept that we are interested in. That is, it may refer to a service interface, a service operation, a non-functional property, etc. The query further specifies constraints on the values of the variables. In this example, the query refers to the airport role of our choreography. We have constraints on the names of the required service interface and the names of the interface operations. These names should be similar to the ones that characterize the airport role. The availability of the required services should be high. And now let's see our queries in action. To execute a query, we move to the Query Edge tab of our tool. We select our query, and then we execute it. The query returns a functional abstraction that represents a set of concrete services for the airport role. For each concrete service we have several useful information based on which one of the services shall be selected for the synthesis of the managed unexpected arrival choreography. In particular, we have the URI of the service, the estimated availability and response time. More importantly, we have the URI that points to an LTS that specifies the behavior of the service. This behavioral specification is used to verify that the service is compatible with the airport role. Let's access the context of the LTS behavioral specification. So here we have the states, the transitions between the states, and the operations of the concrete service that we discovered. Here we have another query that concerns the airport speaker actuator role. We execute it. As previously, here we have a functional abstraction along with corresponding concrete services whose behavioral specification should be verified. At this point, the role of the service discovery is over. Next, the synthesis process takes over to finalize the synthesis of the choreography.
Going back to the synthesis process, after a set of concrete candidate services have been discovered, the synthesis process has to select them by checking for each participant if its expected behavior can be simulated by some candidate service. Note that for a given participant, behavioral simulation is required since the discovered candidate services for it are yes able to offer and require at least the operation needed to play the role of the participant, but one cannot be sure that the candidate services are able to support the operations flow as expected by the choreography. Thus, in order to simulate the expected behavior of a participant with the behavior of a service, the synthesis process uses the simulation method that takes as input the projected LTS of the participant and the LTS of the service as retrieved by the URI returned by the discovery service. It might be interesting to mention that the simulation method implements a notion of strong simulation suitably extended to treat extended LTS. As already mentioned, simulation features are also offered by the Eclipse plugin we have developed. Thus, considering the CLTS of the airport speaker actuator aggregator and the LTS of one service that has been discovered as a candidate for it, we can see how the developer can interact with the plugin to check if the CLTS is simulated or not. After the services have been selected for all the choreography participants, the main synthesis process can generate the coordination delegates by performing a call to the generate CD service. For the purposes of this demo, the coordination delegates generated for the different participants have been published into our CHOReOS domain. For instance, these ones are the coordination delegates generated for all the participants interacting with the airport. After the coordination delegates have been generated, the main synthesis process performs a further call to generate the choreography specification by giving as input the selected services and the coordination delegates generated for them. Specifically, still focusing on the airport participant, the object returned by this call represents an XML-based declarative description of the choreography that specify the location of the selected services and the coordination delegate artifacts that can be deployed. Moreover, as graphically represented in these two pictures, the XML file also contains the dependency relationships among the selected services and the related coordination delegates. In other words, it describes the architectural view of the considered airport case study that conforms to the CHOReOS architectural style. Then, after deployment, these dependencies are used by the enactment engine to dynamically bind the services and the related coordination delegates. Finally, the synthesis process interacts with the enactment engine in order to create the choreography from its specification given as input, and, as described in the last part of the video, the choreography can be enacted.
Now we are going to show the deployment process of coordination delegates generated by the synthesis process. At this point, the airport web services are already deployed and running. Using an ordinary browser, we can check the wisdom of these web services, in this case, the airport service. Each TEDDIE is delivered as a tar.gz package file. Inside this package, we have three files. The LTS file, which describes the CD behavioral description. The WSL file, which defines how the CD will be consumed as a service as any other subservice. And the config file, which provides instructions to the EASB about how to deploy the coordination delegates. Besides generating the coordination delegates, the synthesis process also generates a choreography specification in XML format. This XML will be used by the synthesis process to invoke the enactment engine. Here we will do this invocation using Poster, a simple HTTP client. So now, we will start the enactment engine and also the service deployer and the node pool manager. We have here the service deployer configuration file. It has two important properties. One of them is the cloud provider. Here we make node pool manager create cloud nodes using the Amazon Web Services. The other property is the node allocation policy. What we are saying here is that every time a service deployer receives a request to deploy a service, it will create a new virtual machine to deploy such service. Let's start then. Here, I am starting the service deployer and the node pool manager. And now we are starting the enactment engine. This is the address to invoke the REST operations exposed by the enactment engine. So let's scope our XML into the poster. Before, let's take a look in our Amazon EC2 console. Here we don't have any virtual machine instances created right now. Let's back to the poster and send the request. Here, the enactment engine has already received the description and generated an ID to the choreography, that is the ID1. To really enact the choreography, we have to make one more invocation, like this. Let's post again. The enactment process involves deploying all the coordination delegates and telling web services where their CDs are. All this process takes about 5 minutes. So let's wait a while. Here it is the response provided by the enactment engine. We can have a better visualization here. This response provides details about where each CD was deployed. Here on the Amazon EC2 console, we can see that several virtual machines were created. Let's log in one of these machines. Let's choose this one, for instance. So, now we are logged in, a virtual machine created by Amazon Web Services. Here we can see several files scoped by the enactment process, like for example, the config XML file. An important file here is the ESB client log. Let's see it to check out what has happened in this machine. Here we can see that the CD deployment was okay. Every cloud node created by the enactment engine is also managed by Chef. Chef is an open source configuration manager maintained by the Opscode company. We have set up our own Chef server at USB. So here we can see, for example, the nodes managed by our Chef server. These ones correspond to the nodes created on Amazon. So we can choose one of them, for example, and check its configuration. Here we see that this node has received this specific coordination delegate. Finally, let's check our choreography working. We are going to use a SOAP UI, that is a SOAP client. Let us first invoke the getApproachConfirmation operation on the air traffic control service, and it returns false. Now, let us invoke the startChoreography operation. That will invoke the IAport service. That will invoke many other operations in the choreography. It takes some while. Here we have an empty response. But if we call again the operation in the air traffic control service, we will get true. So, we have here our choreography working.